Look closely at the mechanics of modern industrial agriculture, and you will find an industry locked in an escalatory arms race. Millions of gallons of synthetic chemicals are blasted across monoculture fields every day, deploying raw chemical force to achieve a single goal: total eradication. But pull back the lens and travel to the heart of Lancaster County, Pennsylvania. Here, Amish orchards thrive off-grid. No diesel-powered spray rigs, no synthetic chemical contracts. Yet their crops stand pristine, virtually untouched by destructive pests. This is not a triumph of folklore or luck. It is a masterclass in biological engineering. The Amish do not fight pests with chemistry. They outmaneuver them using passive fluid dynamics and behavioral biology. They weaponize the insect's own evolutionary programming against them. Today, we are stripping away the myths to examine the exact mechanics of this century-old off-grid defensive system. More importantly, we are scaling it down, translating this macro-agricultural logic into a precise blueprint that any everyday grower can deploy in a suburban backyard, a concrete patio compound, or a micro-scale balcony garden. Zero electricity, zero commercial chemicals, and absolute biological control. To understand why this traditional method is so profoundly elegant, we must first diagnose the catastrophic failure of modern consumer pest control. The average backyard gardener faces an immediate disadvantage. When pests arrive, the knee-jerk reaction is to head to a big-box store and buy a plastic bottle of broad-spectrum synthetic pesticide. But this creates what biologists call the chemical treadmill. Broad-spectrum sprays are indiscriminate killers. They eliminate the aphids, but they also wipe out the local populations of ladybugs, lacewings, and predatory wasps, the very apex predators nature provided to keep the ecosystem in check. Because pests reproduce exponentially faster than their predators, the garden is left completely defenseless, requiring stronger, more frequent, and more expensive chemical interventions. Driven by a desire to avoid chemicals, well-meaning growers turn to retail alternatives, yellow sticky traps and electronic zappers. Yet from an engineering perspective, these are fundamentally flawed. Sticky traps degrade rapidly under UV radiation, wash out in the rain, and quickly become coated in airborne dust, rendering them useless within days. Worse, they are untargeted, frequently trapping and killing essential native pollinators like honeybees. For those operating in confined urban environments, such as a concrete compound or a third-story balcony, the crisis is amplified. In these isolated microenvironments, there is no natural ecological buffer. A single pest infestation can decimate a container garden in 48 hours, and spraying airborne toxins in close proximity to living spaces is a profound safety hazard. The modern marketplace insists that the solution to pest pressure is a continuous stream of consumer consumption: more plastic, more chemicals, more capital. But the historical record reveals a different truth. By shifting our focus from chemical eradication to behavioral manipulation, we can build a passive, highly selective interception system that costs pennies, lasts indefinitely, and works with the absolute precision of evolutionary biology. To understand why this system functions with such devastating efficiency, we must look past the rustic surface and analyze its chemical and biological architecture. At the core of the Amish method is a process of intentional, anaerobic fermentation, a controlled chemical reaction designed to exploit a specific vulnerability in pest biology. When sugar, water, and wild yeasts collide, they kickstart a metabolic process that breaks down carbohydrates into alcohols and carbon dioxide. As this liquid ferments under the sun, it releases an ultraspecific plume of volatile organic compounds, or VOCs. To an insect, these airborne molecules do not smell like a trap. They form a precise chemical mimic of overripe, bruised, and rotting fruit, the ultimate evolutionary signal for feeding and egg-laying sites. This is where the behavioral biology becomes highly targeted. For destructive pests like the codling moth, fruit flies, and climbing cutworm moths, this olfactory signal is completely irresistible. Their highly sensitive antennae lock onto the plume, drawing them inexorably toward the source. However, the Amish system introduces a critical chemical barrier: apple cider vinegar. The acetic acid in the vinegar introduces a sharp, sour note that acts as a powerful behavioral repellent to essential native pollinators like honeybees, ensuring they veer away entirely. But the olfactory decoy is only the first half of the engineering equation. The second half relies on fluid dynamics and structural geometry. Traditional Amish traps utilize a wide-bodied glass or ceramic vessel that tapers drastically at the neck. When an insect follows the thermal scent column downward into the container mouth, it enters an expansive inner chamber. Once inside, the insect's natural escape instinct dictates a vertical upward flight path. Because the exit hole is restricted and sits directly below a wide, dark perimeter ceiling, the insect is trapped in a biological loop, flying upward into a structural dead end. Exhausted, it eventually falls into the liquid below. Under normal circumstances, an insect's hydrophobic exoskeleton allows it to float on water. To defeat this, the Amish formula relies on natural saponins, or a single drop of surfactant, which completely collapses the water's surface tension. The moment the insect touches the liquid, it sinks instantly, securing absolute containment. To translate this macroagricultural masterclass into a micro-scale backyard defense system, we do not need expensive materials or heavy machinery. We can replicate the exact structural geometry and chemical matrix using everyday upcycled components right on a balcony workbench. The physical modification of our vessel requires geometric precision. Take your clear 2-liter bottle and measure exactly 2 inches down from the base of the pouring neck. Using a sharp utility knife or a drill, pierce the plastic to create a clean, uniform entry port exactly 1/2 inch in diameter. Repeat this process on the exact opposite side of the bottle. This specific sizing is critical. It is large enough to allow maximum VOC vapor distribution, yet narrow enough to preserve the microclimatic thermal draft inside the chamber. With the containment chamber modified, we assemble the chemical matrix. The ratios must be exact. Measure out 8 parts of dechlorinated water, approximately 2 cups, and pour it directly into the base of the bottle. Next, introduce 1 part dark molasses. The heavy, unrefined sugars in the molasses provide a long-lasting carbon source for the fermentation process, ensuring the trap remains active for weeks without drying out. To anchor our biological barrier, add 1 part raw apple cider vinegar. Finally, introduce a single, small pinch of active dry yeast to kickstart the anaerobic reaction. Swirl the container gently until the molasses completely dissolves into a uniform, rich amber fluid. To complete the fluid dynamics loop, add 1 single drop of standard, unscented dish soap to eliminate the surface tension. The final step is strategic vector placement. Loop your jute twine tightly around the neck of the bottle. If you are protecting a suburban raised bed or fruit trees, hang the trap approximately 4 to 5 feet off the ground, nested deeply within the shaded interior canopy where pests seek shelter from the midday heat. For a concrete compound or a balcony garden, place the traps directly along the outer perimeter walls or balustrades. By creating a defensive perimeter, you intercept flying pests at the boundary line, drawing them into the decoy matrix before they ever make contact with your crops. When you look past the immediate gratification of a pest-free harvest, the true mathematical return of this system becomes undeniable. By replacing a continuous cycle of retail consumption with a passive, upcycled biological decoy, you exit the chemical loop entirely. Over a lifetime of growing, this translation of Amish logic saves hundreds of dollars in synthetic inputs, eliminates plastic chemical jugs from our landfills, and preserves the vital native pollinator networks your local ecosystem relies on. This is the essence of true self-reliance. Sovereign cultivation isn't about purchasing the newest green tech or industrial-grade gadgets. It is about reclaiming an elegant, historical engineering logic. It is the realization that a backyard, a concrete patio, or a balcony is not a battlefield to be sterilized with chemistry, but a delicate biological machine to be gently steered with physics and behavior. If you value this analytical, deep-dive approach to historical engineering and backyard resilience, consider subscribing. We dismantle the fluff to give you the exact blueprints for self-sovereignty, because if you think controlling insects with fermented sugar is ingenious, wait until you see what happens when you harness the thermal power of forest floors. But that is a story for next time, when we decode the secret, black gold, leaf mold Amish farmers make every fall.